In the last short video, we looked at a motivating example for the idea of a graph solving the Königsberg bridge problem. And now I want to take some time to develop some terminology that we use to describe graphs. So we've already talked about the ideas of vertices and edges as being points in a graph and lines connecting those points. So I want to also talk about some particular nice kinds of graphs. So on the left here, I'm going to draw an example of a graph that we will come back to illustrate these different ideas. So this is a graph with 5 vertices. Typically, we give our graphs capital letters for names. So I'm going to call this graph capital G. So capital G has 5 vertices. And frequently we'll label the vertices of our graph with lowercase letters. So I'm going to call these vertices A, B, C, D, and E. And then I'll draw in some edges in my graph. Like so. And so it happens that this graph also has 5 edges. This is what we call a simple graph. So in the Königsberg problem, we had a graph that had multiple edges between 2 vertices. We saw, for example, here, there are 2 edges that connect vertices W and X. In this graph G on the left, each pair of vertices has at most 1 edge between them. So this is what we call a simple graph. There are no multiple edges and no what we call loops. So a loop would be if I had another edge that, say in red here, that connects E to itself. That is a loop. And usually we're going to think about graphs that don't have loops. The degree of a vertex is just the number of edges connected to it. So, for example, in G, we see that the degree of A is 3, the degree of B is 1, the degree of C is 2, the degree of D is 3, and the degree of E is again 1. And we say the vertices are end vertices if they have degree 1. Or an end vertex if we're only talking about one of them. So B and E are each an end vertex in G. We also talked about moving from one vertex to another in that Königsberg problem, and we call that a walk in our graph. And the easiest way to think about a walk is just we're going to list vertices and edges. in order. Let's say maybe in order of traversal. So maybe let me give my edges labels. Yeah, I'll give my edges labels. So these will be 1, 2, 3, 4, and 5. So one walk in my graph might be to go from A along edge 2 to D, and then along edge 5 to E. So in blue, we have the walk A to D 5E. Or, because we don't have any multiple edges, we could specify a walk just by saying the vertices that we're going to walk between. Since there's only one possible edge to go from A to D. And the same between D and E. And so our question in the last problem was really a question about what kind of walks can we find in our graph. And particularly nice walks are cycles where we start and end, a closed walk, sometimes we call those cycles, we start and end at the same point. And so one example of a cycle in this graph and I should say we usually want to avoid repeating edges in a cycle. And there's one cycle in this graph, which is the one containing vertices A, D, C. So we might go A to C, and C to D, and then back to A. So A, C, D is a cycle. And then back to A. So A, C, D, A. The first fact that I want to convince you of about all graphs has to do with the degrees of all of the vertices. Oops. I'm going to call this a proposition. And it says the sum of the degrees of the vertices of a graph is twice the number of edges. And we can see for G, this works out. If I add up the sum of my degrees, I get 3 plus 1 plus 2 plus 3 plus 1, which is, let's see, 6, 8, 10. and G has 5 edges, which is, multiplying that by 2 also gives us 10. So this works out for this example graph, and the reason why it works in general is just that each edge adds 1 to the degree of the vertex at either end. So each edge contributes 1 to the degree of the 2 vertices it connects. So if we add up all of those degrees, we're going to get, we'll count each edge exactly twice.